In IoT, data is generated predominantly by sensors. This data is collected, cleaned, and collated in either edge, fog, or in the cloud. Data can be processed either real time or in archival fashion to derive different types of insights. Each of the components we identified earlier in the architecture lesson, we need to program them individually to perform data management in each of these nodes. The responsibility allocated for each node could be different from application to application, and even within a single application, the responsibilities may change depending on the context. For example, in the same application, you might process data on the edge when 3G communication is not available or is disconnected from the edge device. And as soon as the connectivity established again, you might be sending data to the cloud for further processing. IoT applications tend to generate large volumes of data than any other mobile, web, or desktop applications. It opens up a lot of opportunities where you can extract insights and knowledge. However, it makes the data management analysis much more difficult. In these two slides, I have visualized the data generation by different sources. Each of these figures visualize the scale of the data generation. For example, it says that 90% of the world's data today has been created over the last 2 years. And it also talks about how much data produced in a day. 500 million tweets sent every day, 294 billion emails every day, and so forth. So please pause this video and spend some time to go through this visualization to understand how different sources generate data today. Data science workflows can be visualized in many different ways. However, all of them seems to have very similar phases. First, you start with a question, and then you need to determine what kind of data that you need in order to answer the question. So then you need to go and acquire this data. Then you will need to wrangle the data manipulation, cleaning, data discovery. And then you have two approaches. One, you can use mathematical and statistical models. The other approach is use machine learning. After that, you can produce data reports, visualization, and data products. This is the typical workflow of a data science. Most of the non-technical people tend to underestimate the capability of data science. So here we are talking about a use case related to Target, where based on the products someone buy, the Target was able to identify a particular individual is pregnant before even the family members get to know that. How they do is that they look at the past data where people have what they have bought just before the pregnancy. And then by looking at those patterns, they can determine when someone is being pregnant or not. This is not necessarily an IoT use case. Probably in the lesson 1, you have seen a number of IoT related predictions where you can predict when the particular component in a wind turbine is going to be burnt out, or particular component in a vehicle that will be worn out. These predictions are quite important because, for example, for the manufacturers or the managers of the wind turbines can actually order the components beforehand before they get broke. So as soon as it get broke, the parts can be replaced. Otherwise, when a particular component accidentally broke, you have to order and wait until they are delivered to put back the wind turbine, and then you are going to lose lot of time in between that. Let me now introduce the data science life cycle. The life cycle comprises of 7 phases: business understanding, data mining, data cleaning, data exploration, feature engineering, predictive modeling, and data visualization. First, you need to ask a relevant question and define the objective of the problem that you are trying to address. Then you need to gather and scrape the data necessary for the project. Follow up by data cleaning, fix any inconsistencies within the data, or handle any missing values. Then you need to hypothesize about your defined problem by visually analyzing the data. Then you need to think about what are the important features and construct more meaningful ones to be used in the machine learning algorithms. Which means that you need to identify the features that impact the machine learning models more than any other features. Then you need to go and pick a suitable machine learning algorithm, a model, and then you need to evaluate and test the performance and make sure that you pick the best one. Most of the time, you need to visualize the data to show it to the stakeholders by plotting or interactive visualizations, because most of the people cannot understand just tabulated data. So visualizations make it easier for anyone to understand. On the other figure, I have illustrated how much time each of these phases take. So phases I have put in this figure is not necessarily exactly one-to-one match. But you can get a rough idea what kind of stakeholders are involved in each of these phases and how long they usually take within the data life cycle. When you come to data collection, there are 2 primary sources. So one is the public data, the other one are the private data. So the public data are the data where is available for public. Most of the time, governments are releasing data about their cities, usages, or any information that they usually gather by spending public money. As long as they are not security sensitive or any data that could be used for malicious activities, they tend to release this data. So US government release their own data, UK government also release data. Other than that, government organizations like NASA or any other medical institutions release data for common good. So the idea is that many people who traditionally cannot afford to collect data by themselves, can access to this data and do processing and derive more knowledge than the original collectors have been able to do. Because if one person is looking at one particular data set and extracting certain amount of information out of that, and if tens of thousands or hundreds of thousands people looking at the same data set, there will be more creative people looking at the data set from different viewpoints, might be able to generate more valuable insights than the initial one person. So that is why most of the time, if the data is less security sensitive or privacy sensitive, most of the government organizations tend to release the data. The other data type is private data, where people own their own data. There are a lot of open data related to IoT as well, especially environmental related sensors that collect data from large cities and geographical areas. you can access these data for free of charge. For example, weather APIs provide the data gathered from weather station around the country as well as around the world. These data sets can be accessed either using APIs, or you can directly download the entire data set once. If you are getting access through an API, you will need to query the API regularly to get the latest data sets. IoT products we use every day generates and captures large volumes of data. For example, activity trackers such as Fitbit, or sleep trackers such as Bedit, or even coffee machines collects large volumes of data about our behavior. So we broadly, all of these data we can consider as private data sources where the access is pretty much limited. So we have the access to our own data, and then the companies who manufacture these devices have access to this data. Additionally, every time we interact with the outside world, we generate some amount of private data related to energy, public services, self-measurement, health, public banking and finance, retail, web services, communication and media. So all these companies behind these activities also generate private data. So private doesn't necessarily mean that they are personal, but they're private. So it could be collected by organization where they use the data to provide a service to their customers, but the data is not available for public use. So here it is important to understand that private data is the bigger umbrella. Within that you can see personal data, but there are other data types other than personal data which comes under the private data sources. If you remember the lesson number 2, we talk about sensing as a service, where we imagine a marketplace where we will be sharing private data for external parties in exchange for rewards. There are a significant number of privacy challenges related to big data, but we will be discussing privacy issues later in a different lesson. Here I would like to highlight some of the data types comes under protection in the GDPR law, which is the law that governs the data protection in Europe. The reason we discuss GDPR is that it is the fundamental law that has been the foundation for other legal proceedings developed by other countries. In GDPR, there are 2 categories of data: personal data and sensitive personal data. Personal data is any information that helps to identify a particular person. For example, name, location of data, identification of numbers, IP addresses, cookie data, RFID, or any other data which we can combine together to identify a particular person. Sensitive personal data are the data types that are quite sensitive nature. For example, you need to provide higher level of protection for these sensitive data types, such as health data, general data, biometric data, racial and ethnic data, political opinion, and sexual orientation. Further, it also includes religious and philosophical beliefs and trade union memberships. We previously discussed about the workflow of data science projects. So data science usually start with a problem, and then you think about what kind of data you need to bring on to address the problem. But what is happening is that nobody knows that what kind of information or insight could be gathered from certain set of data sets. So because of that, there is a tendency to first collect data and then trying to figure it out what can be extracted by analyzing those data. So that is why we are seeing a lot of big data, where we try to collect all the data coming from all types of data streams and trying to put them together and then later figure it out how to process them and how to extract value out of them. So that is the primary idea behind big data. So it is a combination of two different things. They are not completely separated. So usually you might have some overall high level idea that you want to answer. But then you collect data more than necessary to solve that particular problem, thinking that you will be able to extract more value out of that if you collect more data. So that is the debate we have at the moment in IoT community, where we try to collect a lot of data, and sometimes it is infeasible to collect and store all the data because there are large volumes of data. Increasingly, in most of the domain, we feel the necessity to filter out and store the data, store the most important data rather than store all the data. Big data is always explained with a concept called either 3 V's, 4 V's or 5 V's. So the common approach is 4V. So that is why I selected the 4V approach. The 4V means volume, velocity, variety, and veracity. Volume refers to the scale of data, how large is data. Velocity is how fast data items are coming in. Variety refers to the different types of data, like social media data, video data, text data, numbers, a different heterogeneous set of data. Veracity refers to the uncertainty of data, poor quality data that sometimes cannot be trusted. All 4 of these aspects bring challenges to the data analysis. As I mentioned before, volume refers to the size of the data. Any application domain could generate large volumes of data. So for example, if it is a retailer, you might have information about all the transactions. But then you also track what kind of products they bought. Especially if this is an online retailer, they may track the information, what are the products you browse through before you bought. So these, and then how long you did the browsing, what are the links did you click. So all these contextual information, which we also call metadata, will be stored. And then if you are serving millions of customers, these data become large, which we refer to as big data. This is a non-IoT example of big data. This is another example for a large volume of data, but here we are talking about sensor data, which broadly comes under IoT. So this is a square kilometer array being built in Western Australia. Square kilometer array is a radio telescope that generates 1.2 times 10 to the power 10 terabytes of data per each year. The amount of data captured is so large that not all data items will be stored, because it is impossible to store all the data generated by the SKA on the side. Nor it will be possible to transmit it to the desert to a nearest city. Therefore, when the volume goes very high, we need to make a decision on what and how much data to be stored and processed. IoT sensors collect a variety of different data types. For example, temperature and humidity would simply capture numeric data. And then camera images and audio sensors and microphones create images and audio signal waves, which of course converted into numbers at the end. However, they are images and audio that need to be treated separately and processed differently than processed temperature data. Then you might want to combine some other data types such as social media data in conjunction with temperature or humidity. So in that case, you need to be processed and prepared that social media data separately. Then your IoT application might also have some kind of customer satisfaction or some kind of a rating data captured from different types of devices such as welcome robots or any kind of infrastructure deployed in a museum. So then those kind of ratings need to be processed separately than compared to temperature or video data. So when you collect a variety of different data types, they need to be prepared separately and they need to be combined together in a meaningful way, because sometimes it has to be attached to a space, a particular geographical location, because if you are talking about satisfaction or giving a rating a particular place within a museum, then you cannot allocate it to the entire museum because it is very contextual for a specific specimen. Therefore, all these different types of data has a space value and a time value. And then they need to be curated and filtered and pre-processed separately before they combine together. This is a significant challenge when you are collecting quite different types of data. More importantly, you need to capture the contextual information or a metadata in order to understand from where these pieces of data has been captured. For example, if you are getting a complaint that someone saying it is too cold, without any context information like what is the cold means, what is the temperature number, and at what time that happened, on what location. If you don't have those information, you can't look into the database or data store and make a determination what is exactly going on, whether the person is experienced something they should not have experienced, or is it something that this particular person preferred a different temperature. Therefore, the context information plays a significant role when you're combining a variety of different data sets. Velocity refers to the speed that the data items come into the system. In a typical non-IoT example could be online transactions. So when the holidays come in or Christmas, more and more people are buying things online, which means that during that period, large volumes of transactions will happen, and then all information and metadata about each transaction will be coming into the system. So you should be able to process, and from banking application sides, they need to worry about the detecting any fraudulent activities. So now you need to have more computation power to do the traditional fraudulent activity detection algorithms by looking at different transactions and buying behaviors. But you need to do it with data that comes very, very fast. In IoT example, you might have a agricultural field where you have sensors, and you may have configured it to increase the sampling rate if there is snowing or any other condition is met. The sensor network will dynamically increase the sampling rate. For normally they may send every 2 seconds, but if the temperature goes below -2, perhaps it might start to send every 2 seconds. So you can closely watch a particular agriculture field, especially if you are growing for experimentation, to identify how the particular seeds are performing in particular climates. So if you are working on a research type agricultural field, you might configure it to change the sampling rate to a higher rate if the certain conditions are met, so you can gather more data and analyze them closely. So in this case, when these conditions are met, your IoT system will see large volumes of data coming quite quickly in high velocity. So your system should be able to handle them. Veracity refers to the uncertainty of data or the poor quality of data. In lesson 3, we discuss about errors that could happen in sensors. There are many different errors. In addition to the errors, you could also have sensors displaced, shifted or dislodged due to the nature or animals or any other factor. So when this happens, sometimes the value could be invalid. However, we may not know until we go and check it. Especially if the sensors are deployed in remote areas where nobody go and inspect them often, then until such inspection happen, you might be receiving incorrect data. Then you should be able to handle or identify those errors or issues. Otherwise, the insights you extract from the data could be wrong. You might also see that sometimes some data items may be missing, some sensors may be stop sending data. So you might have incomplete data set. For example, you might have humidity data but not temperature data, so you have to deal with the missing values. The more number of sensors you have, higher the challenge is, because any of these sensors could go wrong at any time without you knowing them. There are 2 data management approaches that can be used to mitigate some of the challenges posed by big data. Sometimes people think that just because they collect data, they need to store all the data as well. This is not necessarily true. Often though, there are certain key facts or information that need to be stored and maintained. However, it is not necessarily to store all the data. For example, supermarket chain don't have to store every transaction, but can aggregate them in a way that retain the data company requires in a much more compact way. The 2 useful approaches are pre-processing and metadata creation. Both are quite important to address big data challenges. In IoT, sensors collect data in one location and then send to another location for storage, and then maybe another location for processing. The problem is that due to the combination of the volume and the velocity, it is quite difficult to send data across a network all the time, and then also to store large volumes of data. What you can do is use pre-processing techniques to reduce the amount of data that need to be transferred. For example, let's say you have a video and audio based sensors. You don't need to send data when there is nothing happens. For example, you can analyze each image frame, and if there are certain activities happening, then only you can send the data. You can do the same thing, like you can have a motion sensor, and then temperature and humidity and whatever the other sensors might only send the data if you detect a motion in the location. So likewise, and then you can also do some kind of pre-processing such as aggregation, averaging, data minimization techniques, or maybe some kind of sampling rate reduction to reduce the data communication and storage. You can average rather than sending every second. You can average the data over 1 minute and send the average data. Or you can send data when there is a change, like if it is temperature is same, you don't need to send it again and again, and when the temperature changes, then you send it. So likewise, pre-processing is an important part to handle with the large volumes of data that comes from high velocity. Metadata creation also helps to deal with big data. So data is processed, we are looking for particular patterns or for particular evidence. So we analyze the data, extract some information, and then store them. However, when we want to query them back at a later date, we need to know what is the context of that particular data has been acquired. For example, we may want to know what kind of sensors has been used, what kind of location, what kind of time, what are the other sensors were deployed around this particular sensor. When did the sensor calibrated last time? Because if some of the data coming from sensors doesn't make sense, especially if you're looking at that part of the data at a later stage, you might not be able to verify. But if you look at the metadata, if you can capture and store them, like, okay, this particular sensor has been serviced, or the batteries has been changed on this particular date, someone has physically administrated that or inspected that in a particular date, then you can trust it. Because otherwise then you can think about discarding data, because sometimes it could be anomaly, or sometimes it could be just wrong data or poor quality data from a poor hardware. So metadata is important to be attached to data collected from sensors, and also metadata need to be attached to the knowledge you extracted. So you are looking at the knowledge later on, you have the full context to use it in a different data analysis task. Especially when you are dealing with large volumes of data, when you are querying the data at a later stage, it could quite a lot of resources to query that. But if you have some metadata, then you can narrow down your search quite quickly by saving computation resources that is used for querying. Let us now explore a use case scenario related to a smart sprinkler system to find out what kind of programming do we need to do to develop an IoT system. With regards to a smart sprinkler system, one of the first tasks you need to do is, first you need to find out the weather forecast and try to find a way to access them. Because weather forecast allows you to determine whether to switch on the sprinkler or not at a given point of time. Then you need to program sensors to detect the moisture level and combine them from multiple sensors and aggregate them. Then you need to do the programming to communicate between the application and the actuator. Because once you analyze the sensor data about moisture level, you should be able to send command to the actuator to switch on the sprinkler. Then you need to program the either cloud or the smart home hub by combining the weather predictions as well as the sensor data, and then make the decision when to do the watering. Then you need to do embedded programming to control the water release and shut off. So these are some of the very elementary and primary tasks you need to do when you're developing a smart sprinkler system. So each of these steps involves some kind of data which you need to gather, analyze, make decisions, and perhaps store them for later usage.